In this video lecture, we're going to talk about syntax-directed translation for LR parsers. Essentially, what we are looking at is how to take a parser and then use it for something useful, like doing actions, producing code, etc. So syntax-directed translation is a way to take parse trees and convert them into some kind of intermediate code in a compiler. The representation of this translation can take many different forms. So once you've done your parsing and you have a parse tree, there are many different ways that you can do this translation. The first is something called attribute grammars, and this is what we are most familiar with because that's what Yak Bison uses and is the most common way to do syntax-directed translation. And this is the one that we'll be focusing on. There's a couple of other ways that one can do code generation from a parse tree. One involves matching different subtrees in a output parse tree. Those are called tree matching code generators. And the other way to do it is to actually think of the tree that was generated as if it's some kind of input and parse that input to produce code. And those are called tree parsing code generators. They were briefly popular, but nowadays it's uncommon to use either of these to do code generation. So we're going to focus on this aspect of syntax-directed translation and cover this in great detail. So what are attribute grammars? An attribute grammar is a way to do syntax-directed translation. It uses a grammar, and then you do some kind of semantic actions against each rule in the grammar to generate code or semantic action. An attribute grammar is a generalization of a context-free grammar. In this kind of context-free grammar, each grammar symbol is associated with an attribute. An attribute can be really anything: string, a number, a tree, any kind of record or object. So for example, it could be a pointer to an object that itself contains links to other objects and so on. A context-free grammar can be viewed as a function that takes a string and produces a derivation. And a derivation is the same thing as a parse tree. Similarly, an attribute grammar is a way of relating strings to attributes, can be viewed as a byproduct of constructing a derivation. So when we want to associate strings with quote-unquote meanings, we can take a context-free grammar and associate it with these semantic actions that produce what we want once we have a derivation. So an attribute grammar can be viewed in another way as a way to decorate or annotate the parse tree with the desired output attributes. And we'll see some examples of how to view a syntax-directed translation in this way. So here's a grammar that's shown over here. And you can see it's a fairly simple grammar. It has addition and multiplication. It has a C token here, which stands for an integer constant. So we assume that the lexical analyzer recognizes these integer constants and provides us with the value for the constant integers that we get in the input. So for example, the input here is 4 plus 3 times 5. And once we finish parsing or producing a derivation and drawing it as a parse tree here, this is the tree that we would get. We get these values that are shown over from the lexical analyzer. So the three integer constants there, 4, 3, and 5, are provided by our lexical analyzer. So the next step, what we want to do is take these values, move them up the tree. So the next step would be to take the value of 5 and move it up to the non-terminal t here, and the same thing happens over here. Notice that this is the same t goes to c rule. It's exactly the same rule that appears in these two different parts of the parse tree. Then the next step would be to take this 3 and this 5, use them to create a value for this node in the tree, right? So we're decorating the tree with the values of these attributes. Multiplying 3 with 5 in this case gives us the value of the multiplication, 15. In order to do the addition, we need a value for the t and the value for the e. So we're going to move this value from t up to its parent or to its left-hand side equivalently, right? So this is the e goes to t rule, and I'm going to move that value up, and I get the value at e is 15. And now I can compute the value at this node here by adding the two children, T and E, these two children of that node, and the end result is 19, which we can then return as the root node attribute. And so it's basically the result of parsing, doing all of the operations that are in this tree, and we get the result of 19, which we can consider to be the sort of semantics of this grammar. So if you look at the grammar definition, we have these different context-free rules. We can associate each of these rules with action, and the action tells us what to do when we have recognized the right-hand side of the rule. So T goes to C, represented by the action $$.val is equal to $1.lexval. So what we're doing here is taking into account the value of this and moving it to its left-hand side, right? So $$ here stands for the left-hand side, T. Similarly, we can do something for the C times T. We take the first value, $1, which is the C here, multiply it with the $3 value. Notice that the value for this T comes somehow recursively by expanding that T and getting a value for some subtree of this non-terminal. Once I have both the value for C and $3, which is this node, then I can compute the value for $$, which is the multiplication of the two. So for each rule, we need some kind of action that is going to help us decide what the actions to do and how to compute the attribute for the root node recursively. So in this one, this is fairly straightforward. We just pass over the value of T over to the left-hand side E. And then this one is also pretty straightforward. All you need is, if I have T and it could be a subtree, and I have a plus and then an E, and I have a subtree for the E, this value here will be the $1, this value will be the $3. We're going to add the $1 and the $3 to get the value for the left-hand side, which is this $$. And finally, the last one is really simple. We have to just take the value of this and pass it on to the left-hand side. And that we can do really easily by assigning $$, which is the left-hand side, equals to $2. We're ignoring the left parenthesis and the right parenthesis, which would be the $1 and the $3 respectively. So what are the flow of these attributes in this expression grammar? If you consider the flow of these attributes, it's always going to be, you can look at each of the arrows I've drawn here. They're always going from the right-hand side, and then there is an arrow, and then there's a left-hand side. It's always going this way, right? The arrows are always directed from the right-hand side towards the left-hand side. And if you think about what that means in a parse tree, that means that the values are always flowing from the bottom of the tree towards the top, as we saw in that example as well. So it's purely bottom up. We compute attribute values of all the children first, the right-hand side, and then we pass the attribute value to the parent or the left-hand side. So these attributes that are purely computed bottom up are called synthesized attributes. And a grammar with semantic actions or a syntax-directed definition that chooses to use only synthesized attributes essentially is always moving the information bottom up. And such a grammar plus the semantic actions together is called an S-attributed definition. And that's just a way to say that S here stands for synthesized, and attributed means it's attribute grammar. So it's just a jargon term to use for synthesized attributes with a context-free grammar. It's just called S-attributed. However, bottom up is not always going to be a solution to all the problems when it comes to semantic actions. Synthesized attributes may not be sufficient for some cases, especially when it comes to some aspects of code generation. So I'll give you some examples. The first example we're going to consider here, comma separated list of identifiers. So it's a grammar that can, so if I have, let's say, int and I have x comma y comma z, semicolon is declaring these three variables as being of type integer. Now when I'm inserting these variables x, y, and z, I need to insert it into a symbol table, to store the information that all of these three, each of these is a type integer. So later on when I assign it a value, and if I assign it a floating point number, then the compiler should say, hey, you declared it as an integer and you're assigning a floating point value, and that's not valid according to the specification. So let's consider this particular grammar. We can see that it is able to generate a comma separated list of identifiers, because it first generates a type and then generates a series of comma separated identifiers using ID list. ID list can either be a single ID or it can be an ID with a comma followed by an ID list, right? So in this case, I could have an X comma, and then the ID list will come in and I will get a Y comma, and the ID list would get expanded again, and the last one would be a Z, which would be expanded by the base case of this recursive rule, which just says ID list goes to ID. And then this part over here, the type and the semicolon, get added by using the var declaration context-free rule. So let's take an example input. In fact, it's the same one that I used as an example in the previous slide. And this is the same grammar that we had in the previous slide. And let's look at the parse tree for this input. You can see that the parse tree would look like this. We have var declaration, which has a type and a semicolon. And then there is a recursive ID list call, which expands ID list to ID list. And each time it does that, it has an identifier with a comma until we get to the base case, which is the Z. Now, if I look at this X or this Y or this Z, and I ask the question, what information do I need to put this variable, this identifier X, Y, and Z, each of them, into the symbol table? Well, I need to know their type. I need to know this integer, the value of the type for these variables. So how do I get that information? It's not so clear, right? Because here, if I look at just the information in this part of the tree, there is no information about the type. So in order to get it to where I want it, I have to first take the type value, pass it over from type to ID list. And now I can use the ID list value. I have this now, and I'm passing it from type to ID list, which is its sibling, and I'm passing it down to the X. So now this X can look at its parent and say, my parent tells me that I should be inserting the type of integer into the symbol table. It also passes it down here to this ID list. And the reason for that is in order to take that information and move it down to Y, so that Y also, when it inserts itself into the symbol table, knows that it should be an integer. And it's getting that from this node, right? So this node here, which got it from this node, which got it from this node. So you can see the information is flowing from the sibling down to its children, all the way down until I get the information I need. There's one more step, which is this Z needs to be inserted into the symbol table, and it inherits from its parent, the ID list, the type value. So if you look at the flow of the attributes in this grammar, and in this parse tree in particular, each value is coming from the parent node, except for the first one here. This one is taking the value from its sibling, its left sibling. In ID list, first takes its attribute from the left sibling type. Otherwise, the ID list takes the attribute from its parent, which itself it's a recursive rule, so it's taking it from its parent. So this is the grammar. If I was to write down the actions for this flow of information, I need to get information now from my parent, which in the grammar is the left-hand side. So in some cases, I'm going to have to inherit, that hence the name inherited attribute. I need to get or inherit the information from the left-hand side, also known as the parent in a parse tree. So the first one is the case where it's getting it from its sibling. So $2, which is ID list, is getting the value $1.value, which is type. And so in this equation, you can see that I'm taking the value and assigning it to this .in, an inherited attribute in ID list. When I have a type information, these are pretty straightforward. These are just synthesized attributes, bottom up. I just say that my left-hand side should know that I'm an integer or a Boolean, depending on which rule I'm expanding. So we have one case of an inherited attribute. These are synthesized. These two are synthesized attributes. Now let's look at ID list goes to ID. In this case, we want to insert this identifier into the symbol table, but in order to find the type information, I actually have to get it from $0. So I have to get it from the left-hand side. And this one, again, is an inherited attribute. And finally, when I have a comma separated recursive rule, the ID gets a value from the left-hand side, which is $0. And also, we need to pass it down recursively down the list so that when I get to this rule, I need this value from this non-terminal. And that's why I'm passing the $3.in, the inherited attribute comes from the left-hand side. So this again is an inherited attribute. When I'm inheriting from the left-hand side, I use a $0. And when I'm going bottom up, I'm sending a value to the left-hand side. So the left-hand side is getting a value from the right-hand side. We call it $. So they're both referring to the left-hand side, except $0 is inherited and $$ is synthesized. So we keep those inherited and synthesized separate. Inherited attributes are any attribute that's computed at a node based on the attribute from its siblings or the parent. So it's not bottom up. Typically, we combine synthesized and inherited as we saw in the previous example. So question is, can we convert that comma separated list grammar, or that subgrammar that is for variable declarations that can have multiple comma separated identifiers? Can we convert that to use synthesized attributes? And it turns out you can. So here's a different grammar. It also produces comma separated list of identifiers in a variable declaration. The way that it does it is slightly different. It has, instead of having a right recursive rule like the previous case, it has a left recursive rule. So in this case, type list expands to type list ID, comma, and the recursion, the base case is when the type list ends in a type and then the type is expanded to int and bool. So you can see that in the previous grammar, the type was pretty high up in the tree. Like, you would see int up there, and then you would see a comma separated list, like there was X, comma, then Y, comma, etc. Whereas in this case, what we see is we see a type list where you have X, comma, and then you go down again, you get a Y, comma, and then in the end, you might get a Z and a semicolon. And the type information is right at the bottom of the tree, which is all the way here, right? The int is at the bottom. Here, the right recursive rule, the int was right at the top of the tree. So you see we are accepting the same set of strings, so the grammars are equivalent, but the parse trees look very different. In one case, the type information is at the top and needs to be passed down the tree, whereas here the type information is at the bottom, and now we can just pass it up the tree using synthesized attributes. So let's look at an example. Int x, comma y, comma z, semicolon. It's the same input as before, and as you can see, the type information is over here. What I can do now is pass it up from here to here and go up here. The next step is to pass it up to its parent. So the left-hand side of the rule here, type list, is taking the value from its leftmost child, in this case, from the type list, and then we pass it up. Notice that when I have this integer, I can use it to take this identifier. So this identifier would be x, and this would be y, this would be z. I would insert x into the symbol table, and I know exactly what the type for x would be is integer. Same with this one. This would be integer as well. Finally, when I pass it up to the var declaration, the root node, again, when I insert each of these identifiers, including the z, I know that its type should be, I can just take the type and insert it and pass it up to its parent, right? So if I look at the actions that I need to write, I say here that type list, whatever the value I get for type list, I'm going to pass it to the left-hand side, which is $. So remember, if it's synthesized, I just use $. If it's inherited, I use $0. If I have this recursive rule, this left recursive rule, I can again take the value of type list and pass it to its left-hand side. And notice that this ID here can take this same value. So if I was inserting ID into the symbol table, it would really have just $1.val, which is going to be equal to int. And the same thing, the base case of the recursion, it knows what the type is. The type is produced by taking int, passing it to its left-hand side, or bool, and that gets the value for this $1.val. And that gets passed to this left-hand side. So you can see the actions are all geared towards pushing information up the tree using synthesized attributes. So it's possible that some cases you need to have inherited attributes for various reasons. It could be that you can't change the grammar, or it's more convenient to use inherited attributes. But let's look at what direction is possible if I am interested in parsing from left to right, which is kind of how we want our compiler to work. Is we want a compiler to go left to right and then detect errors, and report them essentially from left to right. So let's consider these two syntax-directed definitions. It's sometimes easier to visualize them as a parse tree, as I've said before. So let's look at A and LM, and let's look at the direction of how the information is flowing in these attributes. So the first one says $1.in is equal to $0.in. So you can see that this L is getting information from its parent A. And then the next one says $2.in is equal to $1.val. So L can be expanded, it can have a parse tree, and then eventually it'll come back with some information that's synthesized from its subtree, and it'll have a value. So it says $1.val, we're passing it to $2.in. So what's happening here is that information is passed over to M, which is $2.in, and that $2.in is going to get passed down the tree to the subtree for M. And then finally I'm going to get a val for M, which is $2.val, and then I'm going to assign it to $.val. So essentially I'm moving that information up the tree to its parent. So M is moving that information to its parent, which is the left-hand side A. Right? So if you look at the way that the information is flowing, something comes in, it goes down, comes back up, goes across, goes down. It synthesizes a value while expanding M. When it gets its value, it passes it back up to A, and then A can be used further by whatever is calling the A, can use that value, right? So A has now a value that it can use. Now let's look at the second case, which is A goes to QR. Now it says $2.in is equal to $0.in. So this is $2 passing the value down to R. It's taking this value and moving it down. And once it's done with it, we get a value created from it, which is val. And this value, val, is then this $2.val is assigned to $1, which then goes down to this parse tree. It's inherited and comes back up to give me a value here, which is $1.val, and then I assign it to its parent. So notice that if I look at this sequence of how the information is flowing, one of these is problematic if we are doing LR parsing. So you remember in LR parsing we go left to right and bottom up. This one doesn't seem to be going left to right. It seems to be going from right to left. So the flow of information is not in the same direction as we want information to flow if you're doing LR parsing. So it's incompatible with this incremental processing. You could do either one. If I was to first do the parse tree and then process these actions, then I could do either one. So both, either one, either option 1 or option 2 are both fine if I first do the parse and then execute the actions. But if I want to do incremental processing, then this one is the only one that can work. This one cannot work because it's not increment. It doesn't process the information in the same way as a LR parser does. In a LR parser, you can still have, as we saw in this case, you can still have inherited attributes as long as the information flows from left to right. And that's exactly what we will define as a way to combine inherited and synthesized attributes. And we call it L attributed. And L attributed is just a fancy word to say we allow inherited attributes as long as the information flows from left to right, sort of top down, left to right. So if I have a production which is A goes to x1 and xj minus 1 xj, and then goes all the way to xn, then if I was to provide information to xj, I can have inherited attributes. I can even have it coming from the left hand side. But if I have any information coming from the right hand side, that's not allowed. So these are allowed, this side not allowed. If your inherited attributes satisfy this constraint, then your syntax-directed definition or your attribute grammar is called L attributed. So essentially these conditions ensure left to right and depth first parse tree construction. A S-attributed definition has no inherited attributes. By definition, it is L-attributed. So every S-attributed definition is L-attributed. And so if I was to use a attribute grammar with a LR parser, I must insist on this property holding. Otherwise, I cannot do anything with it. So every attribute grammar that's used with Yak and Bison, for example, has to be L attributed. Let's look into some details of how we can calculate the attributes in attribute grammar when we're doing LR parsing. So LR parsing, as we know, is inherently left to right. We're always shifting and reducing. And so processing is inherently going from left to right. So while we're doing LR parsing, we can store the attributes on the stack. Whenever we do either shift or reduce, we're going to manipulate. You can think of it as a separate stack or the same stack as we use for parsing, but essentially we can push attributes and pop attributes from the stack, do some computation, and then push a new value back on the stack. For synthesized attributes, it's fairly simple. Is whenever a reduce action is invoked, we store the value on the stack based on the value popped from the stack. For inherited attributes, we transmit the attribute value when executing the goto function, because when you execute the goto function, essentially you're saying, I'm going to pop some symbols and then push the new state, which corresponds to the left-hand side, onto the stack. And so when we do that, it can be used to pass information down the parse tree, essentially. Let's look at an example with synthesized attributes. We'll take a very simple grammar. So this T goes to F, and it just takes the value from the right-hand side, passes it to the left-hand side. T times F, it does a multiplication of $1 and $3, which is the T and the F, right? So it takes T and F and multiplies them. F goes to ID. It looks up in the symbol table what is the value for this identifier, and if it exists, it provides a value to the left-hand side, which is F, and if it doesn't exist, it throws an error. Finally, if I have a parenthesis, I will take this value here and pass it to its parent, which is this action over here. As you can see that every single case is a synthesized attributes. It's always flowing from the right-hand side of the rule to the left-hand side. We take this grammar and we do the usual table construction step, and we can see that this is a fairly simple grammar, so it's just LR0. And now when I use this automaton to parse some input, so let's say the input is open bracket ID, some identifier, doesn't matter what it is, and there's brackets around it, and then there's multiplication, and then another identifier. And for simplicity, we're given the value of the identifier is given in this subscript, which is looked up. We're assuming it gets looked up in a symbol table. So if I'm doing the parsing actions for this, I would shift the left paren, the state for the left paren, shift in identifier, and when I do that, I can look up. So when I do a reduce action here, that's when I would look up the value for the identifier. Let's say the value was 3, and I would take that value and push it onto the attribute stack. it's going to do another reduce to get t. And in this case, what I would do is I would pop the right hand side, which in the attribute stack is the value 3, and then it just inherits it, so it pushes that value back onto the stack. So it doesn't really accomplish much. It pops the 3, pushes it back. This rule f goes to open paren t close paren, and when it does that, it does 3 pops. It takes this value, the $2, and pushes it back onto the stack. So notice that I have this f over here. So this f gets reduced to a t. So what I do is I pop the f, I push it back onto the attribute stack. So far I haven't really accomplished too much, because all this was doing was a bracket around an identifier, right? So, and we're just making sure that we keep the value of that identifier on the attribute stack. So at this point, we finally shift the multiplication. We push that onto the attribute stack, shift the identifier, and then we reduce. F goes to ID. We look up this identifier and we see that the value is 2. So the value 2 is pushed onto the stack. When we reduce using this rule, we pop the 2 and push it back as we did with the previous cases. And finally, now we reduce using the t goes to t times f rule. At this point, we do 3 pops, which is the t, the times, and the f. And the action, so I guess we should go back to the action. The action for t goes to t times f is we take the value of $1 and multiply it with the value of $3. So in this case, I would take this is $1, this is $3, we multiply them, and the end result is 6, and that gets pushed back on the stack. And when we accept, we return what's on the top of the attribute stack, and we return 6. There's a few practice questions for you to practice attribute grammars and syntax-directed translation. This one is a fairly simple grammar that generates binary numbers, but they are binary floating point numbers. So they have a dot there which separates the integer part from a fractional part. And your job for this attribute grammar is to provide the actions that can convert the input binary to a decimal value. And there's an worked out example here to show you how to do that. Well, at least what the math is behind it. What you have to do is unpack the math and put it into semantic actions for this grammar. One thing I would say is you might want to look at the grammar and see what is generated by the part which is the integer part and the fractional part, and see if you can find a simpler grammar which is easier for you to write the semantic actions, and then go to this grammar which is slightly harder. Notice that on either side of the dot, on the left side of the dot, there are binary numbers, so just sequence of zeros and ones, and to the other side of the dot is also sequences of zeros and ones. So the language is identical, but the semantics is not identical. Other practice question I have for you here is, it looks scarier than it is. It's recognizing, so this grammar over here is recognizing functions like exp and log to the base e, minus, multiplication, addition, etc. And what we're doing is symbolic, coming up with this symbolic derivative of the input string. So if my input was exp of x, then the output should be the string exp of x, because the derivative of e to the x is just e to the x, right? So, and if it's a derivative of log of x, it's 1 over x, which is this case. Those are the simplest cases. And then you can also do, just extend this recursively to do multiplication and addition, and a unary minus as well. And this would essentially take an input function, which includes any of these. So each function can actually have a complex argument itself, can be a function. And that's covered by this sort of recursive case. So this one is a little bit tricky to work out. You don't have to simplify the expressions. You can produce the expression in a kind of messy way. Typically, when we do derivatives in math, we end up simplifying it and making it look a little bit nicer to read. You don't have to do that here, at least not at first. So you can ignore the simplification process. Just produce the output symbolic derivative of any input string that can be accepted by this grammar over here.